40. So again, I have a. Say it again.
Can I say something?
Yeah, sure.
Regarding this question.
Yeah.
Previous session we discussed about enthalpy and entropy, and we say if these two parameters is positive, I mean more than zero, our process can be spontaneously. Yeah.
Yes. Yes.
In this question, the reaction can be spontaneously and produce heat and energy.
Right, but yeah. So, but okay. So, but we need to know exact temperature at which temperature it's gonna be spontaneous.
So we can find the temperature.
Right.
And calculate the temperature.
Right, but okay. So, but again, you guys are answering the question, but you are kind of around the direct answer. Okay. Okay. So when we said that enthalpy and entropy, both of them are positive. First of all, it's not like that if both of them are positive, it's automatically spontaneous. It's not like that. Okay, so automatically spontaneous is a process when enthalpy is positive and entropy is negative. So then it's automatically spontaneous at any temperatures. But when both of them are positive, it's not going to be automatically spontaneous. So then we need to find the temperature. But again, when we have entropy and we have enthalpy, these two parameters make that equation you are talking about. What is that equation about? What is the name of that equation? What you are calculating when you have enthalpy, entropy, and temperature? What you are
delta G. We must calculate delta G.
Yeah, so this is what
delta G and temperature.
Doctor, we must calculate delta G, yes?
Yeah, so this is what I'm asking, that the parameter, which is delta G, determines the spontaneity of the processes. What is the delta G, by the way?
Delta G gonna be in negative, less than zero.
Yeah, I understand, but what is itself delta
Doctor,
G? What does it?
First of all, we need to
free
calculate
energy.
temperature.
Yeah, so okay, yeah, so this is Gibbs free energy. Okay, this is free energies of the system. So if you have Gibbs free energy less than zero, then the process is going to be spontaneous. If you have Gibbs free energy more than zero, then it's going to be non-spontaneous. So this is what I'm asking. Okay, so if you have delta G less than zero, so this is what we need to achieve, right? In order to make a process spontaneous. So how to find it out now? So now what you are talking about, we can use that equation. So we have delta G is delta H minus T delta S.
T delta S.
Right?
But firstly, we have to find the temperature.
Right. So what we need to find the temperature at equilibrium. First of all, we need to find the temperature. Okay, wait a second. So we need to find the temperature at equilibrium. So when we have equilibrium, can you say?
What, doctor?
Equilibrium.
So T equal delta H per delta S.
No. Again, let's just say again the same thing. I asked you when the process is spontaneous. We found out that the process is spontaneous when delta G is less than zero. Okay. And it's non-spontaneous when delta G is more than zero. Now I'm asking when the process is at equilibrium, so we do not have any process going on forward and reverse way. So we have, I mean, the processes forward and reverse are the same. So overall process is basically at equilibrium. So when do we have equilibrium?
It depends on temperature.
Doctor.
It depends on, again, of course, everything depends on temperature, but we need to find the temperature, right? How to find the temperature?
Doctor, temperature equal delta H divide the delta S.
Okay, again, okay. So look, we come to that point. We will come to that point, but you need to understand why we're doing this. Otherwise, it's very mechanical. So you will never understand what is happening. So again, I'm asking.
Doctor,
Again,
yes,
I'm asking. We have three situations. You guys
yes.
think a little bit. Don't hurry up. Don't hurry up.
I think I get it. Doctor, when delta G is 0 equals
Yes,
0,
yes.
we
So
can, yes,
wait a
we
second.
can
Wait a
find the
second now.
temperature.
Right, right. Just wait a second. So when delta G is 0, it means that we have equilibrium, okay?
Yeah,
This is what does it mean. So now, instead of delta G, you put 0 here. So you have 0 and you have delta H minus T delta S. Now you can find this T, right?
Yeah.
So T is going to be what?
Delta H divided delta S.
Delta S.
Yeah.
So we are finding the temperature at which the whole process is at equilibrium, okay? So this is what we're going to find. Okay, so what is that T now?
Equal 0.965.
Okay, wait a second. First of all, let's put something for delta H.
198.
Yeah, it's kilojoule per mole.
Kilojoule
Per mole.
per mole.
Okay.
Then what is here?
Joule.
205 joule per kilomole.
So calculate this one.
0.965.
What is the
kilojoule?
unit?
Kilojoule per mole.
Kilojoule per mole.
Yeah.
Doctor, we must convert a unit of delta S.
Okay, so this is what I was talking for so long.
Delta S must be kilojoule, yes?
Yes, so that's the point that you guys need to again, so you need to, if you did it for concentrations when you converted something, why you don't do the same thing here?
Why it's not Celsius? Well, not true. We must convert the unit of delta S.
Yeah, so you need to convert it because you have here kilojoules and you have joules here. So if you do the same, if you continue like this, you will get the wrong answer. So this is why important. So you need to bring everything, all new units, you need to bring to the same table, let's say like that. This is why it's so important. So what's going to be the, after conversion, what's going to be this number?
0.198 joule per mole.
Doctor, how we can convert it? It isn't really, I think.
What do you mean how you can convert it? So this is kilojoule, this is joule.
Yeah.
What's going to be the difference between these two? How did you convert milliliters to liters? Tell me. The same thing is here. So you converted milliliters to liters, right? So now you need to convert. Now you need to convert joules to kilojoules.
Divide 10 minus 3.
Yeah. So you need to multiply this one by 10 minus 3. Okay. Yeah. Or you need to divide it by 10 to minus 3. Okay. So this is what's going to be the conversion factor. So you can either do like this way.
The same convert, yes.
So you put here kilojoule now. So it's going to be kilojoule instead of joule. Okay, now calculate what is the temperature.
Equal 965 65.85. 65.85.
Okay, so what
I
is the
think it's
unit?
wrong because kilomole and
Why?
because of the
Wait.
kilomole and
No,
under
this is not kilomole. This
What
is
is it?
Kelvin. This is Kelvin.
Kelvin. Okay.
Okay, so what is the unit here?
Kelvin.
Yeah, it's Kelvin. Okay, now if you compare this
Kelvin, yes.
and this, do you know what is this one in Celsius? So
1 Kelvin equal 200
minus
73.
273.
it's opposite. 1
Thank you.
Celsius opposite. 1 Celsius equals to 273. It's opposite.
1 Celsius in Kelvin.
Yeah, so if you calculate this one, it's almost like minus 270 Celsius. Okay, it doesn't make sense at all. So once you get this kind of answer, it's very erroneous. So you need to always think, once you get something, you need to think, what did you get? Okay, otherwise you might be in trouble. Right, so that's the answer here. So what is this temperature? So what's happening at this?
3.5 Celsius, I think.
Say it again, please.
3.5 Celsius.
Yeah, so yes, it's about.
How can I find it in Celsius? Can you?
You can just convert it to Celsius. So it's 1 Celsius
Every
is
273
So now this
like
guy
1.
will be about, I don't know.
3.5.
Say it again, please.
3.5.
Yeah, so something like that. I just
Every
need to calculate. But look,
Kelvin.
you don't worry now about Celsius. You have it in Kelvin. You can just keep it in Kelvin. That's okay too. Okay. So what you can do. So what you can do now is that. Okay. So what did you find? What did we find eventually? This time, what did we find? Can you tell me?
We find the temperature.
We find delta H and delta S and temperature. Now we can find the delta G.
No, listen to me. We don't care about delta G.
Now we can know if it is spontaneous or not spontaneous.
Right. So we found the temperature at which we had equilibrium, right? Right?
Yes.
Right.
Okay, so now you need to find the temperature at which it's going to be spontaneous. So what's going to be the temperature? Hello?
I am here, doctor.
All right, so think about what's going to be the temperature. So we found that we have the temperature. We found the temperature at which the process is at equilibrium. Now we need to find temperature at which the process is going to be spontaneous. Think about that one.
If it's above of 3.5 Celsius, it will be spontaneous. If it's
right,
under
exactly.
3,
right,
because
exactly.
the delta H will be positive, not negative.
Right, exactly. So the temperature we can have is that it's going to be more. So let's say like that way. It's going to be temperature must be more than 965.
So delta G must be above of 0, right? If it's spontaneous.
Yeah, no, look, we already determined what's going to be delta G.
Yeah.
Can I say something?
0.
Okay, so the T must be more than this temperature, more than 965.85 kelvins, okay? So if we have more than this temperature, then this process can be spontaneous. That's the answer for this question. Did you get the point or not?
Yes.
Can you repeat the point?
Exactly.
Say it again, please.
Can you repeat this point?
Yeah, so you found the temperature at which the process is at equilibrium. So delta G is 0. So how to make it less than 0? So you need to increase this term, right? So it should be higher than delta G H. How to increase this one? You need to make this T high. So if you have T higher than this,
because when we have a high temperature, the delta S high.
T delta S is high, yes.
Yeah, T delta S high, and delta G is lower.
Yes. Did you get that? Did you understand or not?
Yes. It's the opposite direction in this case.
Yeah, so if you have less than this temperature, then this the process will not be spontaneous. Okay.
Doctor, you mean if the temperature above 965.185 will be spontaneous? Yes,
right. Do you understand why or not?
Yeah, of course.
Okay. All right, so let's just move to the next question. One more question you will have about, do you guys remember we talked about ionic equation, molecular equation, net ionic equation, stuff like this? Yeah, so one more question you will have about that. For example, say you have a reaction like this. So so this is aqueous. This is also aqueous. This is the reaction here is going to be AgCl. It's a solid plus NaNO3, aqueous. So here we have molecular equation. So AgNO3 plus NaCl is AgCl plus NaNO3. That's the molecular equation. Can you remember what is ionic equation here? How can we write ionic equation? Do you remember that?
Yes.
Maybe we can separate the element.
Yeah, so you need to separate this compound in ions.
Yeah, compound.
Right? Yeah, you need to make ions, right? How to make ions from here, for example?
Ag plus 3.
Okay, so why Ag plus 3? All right, so Ag is just 1.
I saved
I
saved.
Okay, Ag is plus. Then we need to add NO3. So what's going to be the charge for NO3?
Minus.
Exactly, it's going to be minus, then plus. So now let's look at here. What's going to be the charge for Na?
Plus.
Exactly, it's Na plus Cl.
Cl minus.
Sorry, Cl minus.
Yes.
Then what is next?
Ag plus.
Okay, so you say Ag plus. Then
Cl minus.
Then
Na plus. NO3 minus.
Okay, so we wrote ionic equation, right? So this is ionic. Can you now write net ionic equation here? Net ionic equation.
Okay, not ionic equation.
Net ionic.
What mean net ionic?
Net means like some summary. I'll say that overall. The final ionic equation. Say like that way.
Yeah, we in this.
All right. So how we make it is that we need to cancel out
We
ions
delete.
from
I
yeah.
think we don't have
Delete
net ionic equation, yeah?
Wait a second.
Delete.
We will come to the point. So we need to delete ions from the
Yeah.
left-hand side,
Yeah.
right-hand side.
Yeah.
Okay,
Don't have
so
net ionic.
let's just delete common ions from left-hand side and right-hand side. So Ag, do we have common Ag from the left-hand side and right-hand side?
Yes, yes.
Yes.
Okay. What about NO3?
And also,
Yes.
yes, we have.
What about Na plus?
We have.
Yes.
We have.
What about Cl minus?
And Cl minus, yes.
So we don't have net ionic equation.
So we do not have a net ionic equation, right? This is what does it mean? Is that true?
No.
No.
Okay, I'm telling you that there is this equation going on, right? So there's reaction going on. Now let's just go back and look everything, what we made wrong. Okay, so can you look carefully what is written here? What is written here? What is written here?
So we have an equation and
Yeah.
precipitation reaction.
Right, so this one precipitates, okay? So you cannot write it like this way.
Yeah.
So it cannot be broken down in ions because it says solid over here.
Yes.
It's S, solid. Now let's look again. Do we have common, which one are common like ions here?
So just we cannot delete Ag plus and Cl minus.
Exactly. So we cannot delete this one. We can delete this,
It's not
this.
net ionic.
So this one we cannot delete. So this net ionic is going to be Ag plus
Cl minus.
Doctor, we cannot delete AgCl because it's solid.
right.
But in aqueous,
Yes.
what?
Yes, we cannot break it in
but-
ions. So we could do
Yeah,
not have
in aqueous, we can delete.
yes.
So
Yes.
just a solid.
Yeah, just a solid. Because we will
When we have the same situation,
what do you
in
mean,
aqueous to aqueous, and if can AgNO3 solids, and in
Okay, so we will study about that one next time about colligative properties because it's very important to know this kind of thing. Because, for
Yeah.
example, if you mix two solutions of NaCl and KCl, there will be no reaction at all, and you will have mixture of all these things in there. But here is definitely there is reaction, and you definitely will have AgCl and NaNO3. So you will need to understand this kind of thing because once we move to the real kind of systems which are related to the living organisms, so then there will be information you will understand why we need to know all these net ionic equations and stuff like this. Okay, so this also, we are not just doing this one only for just know something. We need to use this information. We need to use this knowledge also, and we'll see it how we will use it next after midterm. Okay. Okay, any questions here?
No, thank you.
All right, so now let's just do one more example. Say you have NaOH plus HCl. So the answer here is aqueous. This is aqueous. This is aqueous. And this is NaCl plus this is aqueous plus H2. Oh, this is liquid. Now, can you just write net ionic equation, net ionic equation?
Okay, Doctor. Can I start?
Sure.
Okay, first we separate the compounds to elements, positive and negative charge. Na plus, OH minus.
Okay, let's just write it.
Okay.
Na plus OH minus. Okay, then?
Okay, plus H plus Cl minus.
Right. Then?
Then Na plus Cl minus.
Then?
Okay, H plus O.
Doctor, no, we cannot.
Yeah, we
Oh,
can.
it's liquid.
Yeah.
It's liquid. Okay, it's liquid. Then.
Doctor, then it will be OH minus, H plus, H2O. Give us H2O. OH minus plus H plus. Give us H2O.
Yeah, right. So this was going to be the net ionic. So this is ionic. This is ionic.
Yeah.
And this is net ionic.
I forget it.
Doctor, before we end, can you explain for me from the last lecture what is RT in K, the free energy chemical equilibrium?
This RT delta G is minus RT.
Yes. Doctor, I didn't understand.
Ln K. So this RT is R is universal gas constant and T is temperature. This is a constant number. Okay, so this is a universal gas constant. You're supposed to, I don't know if you studied it or not, but just this is a constant. You just need to remember this is 8.314 joule per Kelvin per mole. Okay, so this is the universal gas constant. This is just the temperature. Okay, and this is the equilibrium constant. So this is about, so when there is reaction, you have reactant and product, right? And you need to have the ratio of reactants and products. So that's the constant we are writing here. And if you know the delta G, if you know, say, you know RT, right? So you can find this equilibrium constant, which is quite important one. Okay. But we're not going too deep in this direction. Okay. All right, so what about ionic equations? Did you guys understand?
Yes, Doctor. Yes.
All right, so one more thing you will have is to write, for example, rate expression.
Doctor, but I can ask you something about it equation. Doctor, if we have aqueous, just separate the aqueous, and the liquid and solid, we not to separate it.
Okay, so if you have solid, you cannot separate it. If you have liquid,
Yeah.
also you cannot separate. You can separate only when you have aqueous.
Yeah. If we have just one of liquid in this in this reaction, we cannot separate it.
Yes, we cannot.
Yeah.
All right, so let's just look another different method. So we need to write rate expression. So kinetics, rate expression. Say you have equation like this. Say you have the equations. Say you have CH4 plus O2. You make C2O, CO2, I'm sorry, plus water. Right, so you have 4, so you need to have 2, and that's it, right? So how to write rate expression for this reaction?
Minus.
Yeah, so this is rate is gonna be minus
delta CH4.
Right, delta CH4
per delta T.
or delta T. Then
equal.
Right.
Minus delta O2 per delta T.
Then
equal
positive.
Right, positive. Delta CO2.
Delta CO2.
Delta T equals
positive delta H2O
per 2 delta T.
2 delta T, right? 2 delta T, right? So the same thing, say if we have Na2 plus H2, we have NH3, right? So we have 2, 3, 2. I'm sorry, we do not have anything here. So for this one, the same thing, right? So it's gonna be delta
minus delta.
I'm sorry, minus, right? Minus
divide delta T.
Delta T, which equals minus delta H2 3 delta T, and this is gonna be 2. I'm sorry, delta
positive delta
NH3 2 delta T. Okay, I think this is clear, right?
Yes.
Well, first, only thing you need to do, you need to balance equation. So you need to balance it, and then everything will be fine.
And we put the moles.
Yeah. So this is moles.
Multiplied temperature. Yes. Doctor?
Yeah, it's not temperature. What is this one?
Sorry, time.
Time. It's time. It's not temperature.
Doctor, expression will be in exam.
Yeah, this kind of questions you will have on exam. All these type of questions. Okay, so one more thing I want to discuss is about percent yield. Okay, you remember we had some percent yield calculations, like we discussed about that one. But I want you to, for example, if we have, let's say, CH4 plus O2, it goes to CO2 plus H2O, right? and we have 2 over here, and that's it, right? And 2 here. I'm sorry, we needed to write 2 over here, okay? So in the previous one, we made a mistake. We needed to write 2 over here. So then it's gonna be 2 over here, okay? All right, so let's say we have something like this, and we produced, say, we have 5 grams of methane. So this is methane, CH4, okay? And say we produced, let me think, 18, just 1 second. Let's quickly do it. I have 1 minute, but please come back when Zoom is off. So just 1 second, give me a couple of seconds. Say this one, we have just looking for words and just 1 second. All right, so, and we produced, let's say, 11 grams of CO2, okay? So the question is that we are given 5 grams of methane, and we produced 11 grams of CO2. What is percent yield? How to find percent yield? So the strategy is like this.
Doctor,
Yeah.
that's volume to volume. Yes.
No, we don't need to take scale volume.
Mass to mass.
Actual yield per
Mass.
theoretical
Yeah,
yield.
yeah.
Yeah. First of all, we need to write what is the yield, percent yield. Okay.
Yeah.
So this is actual yield.
11.
No, yeah.
11 minus 5.